Hi, in this lesson we're going to be looking at eigenvalues and eigenvectors. We're going to start off by trying to get an idea and a sense as to what eigenvalues and eigenvectors are. But there's lots of ways of thinking about eigenvalues and eigenvectors. We're going to take the transformations approach of thinking about this. So I'm going to write down a transformation matrix 3, 0, 0, 2. Okay, so we should have seen from earlier work that this represents a stretch of factor 3 in the x direction, and it also represents a stretch of factor 2 in the y direction. Okay, right. So in this context, we would say that this transformation matrix has two eigenvalues. One of the eigenvalues, so eigenvalue 1 is going to be equal to 3. And the other eigenvalue, so eigenvalue 2, is going to be equal to 2, because those are the stretch factors. Now the eigenvectors, well, there's an eigenvector that corresponds to this one here, so we'll call that evec1, and the eigenvector that corresponds to the 3 is going to be the x direction. And the x direction as a vector I could write down as 1, 0. So that's going 1 in the x direction and 0 in the up direction, or I could have written it as 2, 0 or 3, 0, or any multiple of 1, 0. So an eigenvector 2 is going to be equal to, well, that's the y direction, so I could write down any multiple of 0, 1, so I could have written any multiple of that. So this is telling me that this is a stretch of factor 3 in the x direction, and this is a stretch of factor 3 in the y direction. Now that's basically what eigenvalues and eigenvectors are when we think of it in the sense of transformations. Now I happen to have a stretch in the x direction here and the y direction here, but it doesn't necessarily have to be in the x direction. I could have had a different vector here that was stretching me in the direction 1, 3, for example, or I could have had a different vector here that was stretching in the direction -2, 4, for example. So there was other possibilities of the direction of my stretch. So those are the kind of problems that we would be looking at solving. Now, just to give you a sense of actually what's gone on here, we can have a look at this vector that goes through the origin in autograph, and I can move this vector around here anywhere I want it to be. Now, what I'm going to do is I'm going to introduce our transformation matrix, and I'm going to transform this position vector using the matrix that we had before, that was a stretch of factor 3 in the x direction and a stretch of factor 2 in the y direction. So we're going to have something that looks like that. Now, as you can see, this point here gets transformed to this point here. Now, what happens when I put this somewhere on the x-axis? Well, let's have a quick look. If I put that there on the x-axis at 2, 0, as you can see, that point has now been transformed further down the line, and it's actually 3 times further away down the line at 6. So we would call this an invariant line, because any point along this line transforms to somewhere else along this line. And in a sense, if this is vector 3, 0, this vector here is 3 times as much, so it's a scalar multiple of 3, 0 at 9, 0. Similarly, if I was now to move this point, and this isn't true anywhere else, only along this line that we've discovered so far, but if I was to move this vector over here onto the y-axis, we can see that we've also got an invariant line, and any point that's on this line is mapped to 2 times further away from where it started, therefore having a stretch factor of 2 or an eigenvalue of 2 to somewhere further away on the line. And even if I go down here, anywhere along this line, that's going to be the same case. So there's only 2 places where that happens, along the line, along the x-axis, or the line 1, 0, the direction 1, 0, or along the y-axis, which is the direction 0, 1. So we can use this idea to help us find eigenvalues and eigenvectors in other transformation matrices, which we're going to have a quick look at doing now. Okay, so we're going to try and find the eigenvalue and eigenvector of this transformation matrix here, 2, 5, 2, negative 1. So we'll go over to autograph, and we'll apply this transformation matrix to a vector, and then we'll see if we can find where the invariant lines are, and what the stretch factors are using that. Okay, so here I've got my position vector, and I'm going to transform this using our transformation matrix that we had before, 2, 5, 2, negative 1. Now we can see from this that it isn't going to be obvious which direction our stretches are taking place, and it's not even obvious that there are going to be any stretches. It may be that there isn't a stretch factor at all, so there aren't any eigenvectors at all. So we're going to move this around and see if we can discover any. Okay, so as you can see, this point has been transformed over here, which isn't along the same line as this here. So this obviously at the moment isn't one of our eigenvectors, but if I move this around, hopefully I'll be able to discover somewhere where there is an eigenvector, and there we go. Okay, so we've got one of our eigenvectors, and I'll move it over here, and we should be able to see that one of our eigenvectors is going to be 1, 1, and this point 1, 1 gets stretched to 4, 4. So it's a scalar multiple of 4 away from where it started. So we've got a eigenvalue of 4, and its corresponding eigenvector is 1, 1. So we found one so far already. Okay, we'll see if there's another one. Okay, well that's the same as the one that we had before, because that's just a different multiple of 1, 1. It's negative 1, negative 1. If I come over here, okay, we can see that our line seems to have straightened up over here. So this point, negative 2, 5, has ended up at 6, negative 10. So we've got an interesting eigenvalue this time. Our eigenvector is negative 2, 5. Our eigenvalue is actually going to be a negative eigenvalue, and it's 1, 2, 3. So it's our eigenvalue is going to be negative 3. So let's just go back and jot those down. We had 1, 1 and an eigenvalue of 4, and we've also got -2, 5, and an eigenvalue of -3. So we had an eigenvalue, first eigenvalue was 4, and its corresponding eigenvector was 1, 1. We also had the eigenvalue, which was -3, and its corresponding eigenvector was -2, 5. Okay, so what that means is that this particular transformation here represents a stretch of factor 4 in the direction 1, 1, or the 1, 1 direction. And we've also got a stretch of factor -3 in the -2, 5 direction. Okay, we're going to come back to this in a little while. What we're going to do now is we're going to have a look at some algebraic techniques of discovering what the eigenvalues are and what the eigenvectors are. So I'm going to take you through a little bit of theory behind that first of all. So we'll come back and we'll compare our solutions later on to this solution here. Now, what we're looking for is we're looking for a transformation matrix, which I'm going to call M, that when I multiply it by a position vector xy, I get a multiple of that position vector xy. So I end up with something that's further along the same line. Okay, so in effect, multiplying this vector, this position vector, by this matrix is the same as multiplying this position vector by a scalar quantity. So this is the problem that we're looking to solve in order to find our eigenvectors. Okay, so we are going to start off by rearranging this. So I'm going to write this like so. Whoops. Okay, so take away lambda xy is equal to our 0 vector. Okay, so I can factorize this. So I've got m take away, and I can't take away a scalar quantity from this, so I'm just going to multiply this by the identity matrix, and xy was our common term, so we've got this here. Okay, so this and this and this all mean the same thing, it's just written in a slightly different way. Okay, so I'm going to let m be the matrix A, B, C, D, so I'm going to replace m with A, B, C, D, and lambda I is going to be 0, 0, lambda, and if I times that by xy, I get that there. Okay, and I'm just going to simplify this a little bit, so I'm going to write this as a single matrix. So I've got A take away lambda 0, A take away lambda, B, and I've got C, and I've got D take away lambda over here. So that's my matrix, and if I times it by my point xy, I want the answer to be 0, 0. So we're looking for eigenvalues, which are in this case called lambda, and this eigenvector here, xy, that is going to make this true. Now, this is the bit where we need to give it a little bit of thought. If the determinant of this wasn't 0, so that means that this is non-singular. If this here was non-singular, then an inverse would exist. So I would be able to multiply that inverse by this vector here, which would just give me 0, 0. I'll show you what I mean. So if this was non-singular, then I would be able to do I would be able to take the inverse matrix and times it by this 0 vector here, which obviously is just going to give me the 0 vector here. Okay, but this isn't what I want. I'm not looking for, I obviously know that the origin is going to be invariant, it's going to stay where it is, so that this solution is of no interest to me. I'm looking for when there isn't an inverse that exists. So I'm looking for situations where this here is singular. Okay, so the determinant of that there would need to be 0. Okay, so just get rid of that there. Okay, so we want this here to be equal to 0. And if I solve this here, which is what we call our characteristic equation, the values of lambda would give me my eigenvalues. That would tell me which values would make this true. Okay, so I'm going to go ahead and I'm just going to multiply this out. Okay, so to find the determinant, I do that times that, take away that times that, so take away BC, and that's going to be equal to 0, and I can just write this in a slightly different form. If I multiply it all out, I've got lambda squared, let's take away A plus D times by lambda, you can check this for yourself, plus AD take away BC is equal to 0. Okay, so this here is also known as our characteristic equation. This is the equation that is going to tell us what lambda is. I tend to remember this part here, okay, because this is the key to get us to where we need to be, which is what our values of lambda are. Okay, so what we're going to do is we're going to use this idea to work through our previous problem so that we can discover what our eigenvalues are. Once we know our eigenvalues, we'll have a look at how we can then use that to find our eigenvectors. Okay, so the situation that we had before was we were trying to find the eigenvalues and eigenvectors of this matrix here. Okay, I'm just going to tidy this up a little bit to give us a little bit of room, and we'll leave this here to remind us of our previous solutions. Now, we know that what we're looking for is when A minus lambda b c equal to 0, 0. Okay, this is our equation that we're trying to solve. So in this case here, we can substitute these values in, and we're looking for 2 take away lambda 2 5 minus 1 take away lambda 0, 0. Right. So as we said previously, we would want the determinant of this to be 0. So I'm going to say that I want the determinant of this here to be equal to 0. Okay, so I'm going to write down my characteristic equation for this. So I've got 2 minus lambda take away 10 is going to be equal to 0, and if I multiply this out, I'm going to get lambda squared take away lambda take away 2 take away 10, so take away 12 is equal to 0. So now factorising this and solving this, I'm going to get lambda take away 4 lambda plus 3 is equal to 0. So that tells me that lambda is equal to 4. So that's going to be my first eigenvalue, and my second eigenvalue is going to be negative 3. Okay, just to tidy that up a little bit. Right, okay, so what you should have spotted is that our eigenvalues 4 and negative 3 match here with our stretch factors that we found earlier on. Our next task is to find what the corresponding eigenvectors for this here is. So in order to do this, what we're going to do is we're going to have a look, and we're going to use this here. So this is the equation that we were trying to solve in the first place. We now know the values of lambda here, so we could substitute those in to find what the values of x, y are going to be. So first of all, and I'm just going to start this over here, so we're going to write when lambda is equal to 4. Okay, so when lambda is equal to 4, I could put 4 into here, so I'm going to get minus 2, 2, 5, and that's going to be negative 5, and if I multiply that by x, y, I get 0, 0. Okay, so so that means that negative 2x plus 2y is going to be 0, and 5x take away 5y is going to be equal to 0. So I need to find x, x's and y's that are going to make this true. So looking at this, if x was 1 and y was 1, then that would be true, and this would be true as well. So I'm going to choose the value of 1, 1. So therefore, when lambda is equal to 4, which is my first eigenvalue, then the corresponding eigenvector, which I'll call e sub 1, and that's going to be 1, 1. Okay, now I'm going to have a look at when lambda is equal to and we'll use the negative 3. Okay, so that's our second eigenvalue, and I'll just put a line down here so we can separate that. Right, so so this time I'm going to put negative 3 into here, so that's going to give me 5, 2, 5, and negative 1, take away negative 3 is going to give me 2. Y equals 0, 0. Okay, what you should be noticing is that in our matrices now, the second line is a multiple of the top line, which is what we want. It makes sense. We've chosen our determinant of this to be 0. Yeah, so that's what we've chosen to happen. Okay, right, so I've now got 5x plus 2y is equal to 0, and I've got 5x plus 2y is equal to 0. Okay, 5x plus 2y, 5x plus 2y is equal to 0. Okay, so that means I can choose values of x and y that are going to make this work. So if I chose x to be negative 2, that would make that negative 10, and then y could be 5, so I'm going to say my second eigenvalue is going to, eigenvector is going to be negative 2, 5, and that works. Okay, and remember, it's any multiple of these that would work. I could choose 7, 7 in here, and that would make this true, and it would make that true. Or I could have chosen negative 3, negative 3, and that would have made them true here, and likewise over here, any multiple of those. Sometimes people write parameters outside there to show that it's any multiple. You can use this convention here where you just say any of the eigenvectors. Sometimes people want to write unit vectors here as well, but what we've got here is fine. So again, we've got our eigenvalue of 4 and its corresponding eigenvector 1, 1, which is what we found earlier, our eigenvalue of negative 3 and its corresponding eigenvector of negative 2, 5, which is also what we found earlier. And remember, this tells us that it's a two-way stretch of factor 4 in the 1, 1 direction, and of factor negative 3 in the negative 2, 5 direction. Okay, just before we finish, it's probably worth mentioning that in this particular situation we found that there were two invariant lines because there were two solutions to this characteristic equation over here, and which is what kind of told us that there's going to be a two-way stretch. It may have been that there was only one solution to our characteristic equation, or even no solution to our characteristic equation, which would have told us other things about our transformation, which we would explore those ideas as well in a future lesson. Okay, so that's hopefully given you an overview of what eigenvalues and eigenvectors actually are. If you have any questions about this tutorial, feel free to get in touch. Thanks very much for joining me. I hope to see you again soon.